Hey guys, I promised you that I was going to say a little bit more about homogeneous differential equations and do a little video of an example of this. I didn't quite have time in class to do that. So, well, here we are. I'm just going to kind of refresh your memory real fast and then do a quick example to hopefully help you out with this little topic. So, homogeneous differential equations always can be written like this. So, the derivative of y is some function of the variable x and the function y. So we don't know what it is, but we do know for a homogeneous differential equation, if we attach a t next to every single x and next to every single y, all of those t's should cancel back out again. So just really quickly, here's an example. Let's suppose that my function f of x and y was x over x squared plus y. Okay? Now, if you attach a t next to every single x and every single y, we'll have xt on the top, x squared t squared plus yt on the bottom. And what you'll notice is that while you can factor and cancel one of the factors of t, right, from the top and the bottom, you cannot get rid of all of the t's here. Right? There's still an extra t because this is t squared right here. Right? So this is not f of xy. This one would not be homogeneous. Okay, so this is just a quick example of a function that you could not apply the method of change of variables to it in order to solve the problem. Okay? Let me give you another example here. And so the real question is just, can you get those t's to cancel out, right? That's really the main question. So here's an example. Suppose that you have y prime equals y over x plus the square root of 16x squared minus y squared all over x. All right? Let's just take this example here. So my f of x and y is just right here. It's just this right-hand side. Now, if I attach a t next to every single x and every single y, let's look at what we get. We're going to have yt over xt plus the square root of 16x squared t squared minus y squared t squared all over xt. Okay? And the question is, can you get all of those t's to cancel out? Well, the answer is yes, you can, right? Certainly right here, we can cancel these t's in this expression. Over here, we would need to factor a t squared inside of that radical, and then we're taking the square root of it, right? So this little piece right here, I can write the top as t squared times 16x squared minus y squared, right? And when I look at the denominator of it, you see this t and this t squared can be canceled out. So, indeed, we have something where if we simplify it, all of the t's would go away. So, this is a homogeneous differential equation. We have a homogeneous differential equation. I hope I'm not going too fast, but of course the beauty of these videos is that you can stop and rewind and rewatch as many times as you'd like. Well, that's kind of nice. Well, so remember what I told you guys. The change of variables that you want to use when you have a homogeneous differential equation is this one right here. I use a v for this one. When we were talking about Bernoulli differential equations, I always used a u. Here I'm using v just to really separate this technique from the other one. It doesn't really matter what letter you use. But we are going to want to calculate the derivative of y. And I'm using the product rule to do that. So this is just the product rule. So we have y and y prime, right? And then the idea is just to go ahead and plug in everything we see here in terms of x and v. So on the left side, I have y prime. That becomes xv prime plus v, all right? And then on the right side, notice I have y over x right here. Well, y over x is just v. All right, and then the second term is a little more complicated. I have the square root of 16x squared minus, well, y squared is going to become x squared v squared, all of that over x. We can actually simplify the right side a little bit more. Again, I can factor the x squared, pull it outside of the radical, and cancel it with the denominator. If I do that little algebraic manipulation, I'm just going to get this expression right here. Okay? The thing to notice is the v's cancel right here, which is very nice. And if I rewrite the v prime as dv over dx, well, then this is what I end up with. As advertised, you end up with a differential equation that is separable. So homogeneous differential equations always become separable after you apply this change of variables to them. Okay? So let's separate it. I'm going to divide by the square root of 16 minus v squared. And I have to throw the dx to the other side and divide by the x that was on the top there. So we've got the v's and the x's totally separated now. Okay? So we just have to integrate both sides. The one on the left is actually kind of a standard integral. It would be in any table of integrals that you would have. It turns out it's an arc sine. And what it would be in this case, if you look it up in a table, it's the arc sine of the quantity v over 4. The right-hand side, of course, is the ln of the absolute value of x. And then we put our plus c there. Okay? And try to solve this for v. To do that, I'm going to take the sine of both sides, and then I'm going to multiply by 4. So it's going to be 4 times the sine of the ln of absolute value of x plus c. All right? That's what v is. Don't forget, that's not your final answer. I erased the change of variables, but you need to ultimately write your final answer in terms of y. Well, y is just x times v. So y is just xv. In other words, it's x times what we have right here. So 4x times the sine of the ln of absolute x plus c. There you go. So this would be the final answer. Okay? This is just an example of how to solve a homogeneous differential equation. You first have to make sure that your function is in fact homogeneous. That's how you know that you can apply this technique. And then you have to use your change of variables to substitute the expression into something that becomes a separable differential equation involving v. Okay? Once you've separated it and integrated it, don't forget with your final answer to go back and write everything in terms of y again. So that's about it. I just wanted to share that with you. Hopefully this example will help you to solve other problems on homogeneous differential equations. Thanks a lot. See you soon.